All right, so this is about folds, and the main question is, well, I'll talk about folds and I'll talk about parsers, time permits. So, how would we compute standard deviation of this list of data? Well, we can compute it in a simple way. Compute the length. So this is a list. Compute the length of this list. Compute the average. Compute average of squares. Right? And compute standard deviation. Well, this is a simple way of doing it. There's certainly a more sophisticated way of doing this, which is to introduce a correction factor, which is n divided by n minus 1 due to sample variance. All right, this is it. Now, the problem with this computation is that we traverse this list 3 times. Every time you do a length, a sum, or a map, and so on, you traverse this list. So actually here we traverse it 4 times. Because map traverses and then the sum also traverses. So the way to avoid traversing many times is to formulate these operations as some kind of fold operations. And so let's look at the type signature of fold. Fold left, for example. What is the type signature of that? It takes a value b, of type b, and it takes a function that updates the accumulated value. And so it goes over your list, starting with the initial value b, which is the initial value of the accumulator. And then for each value a from the list, it calls this function to update the accumulated value. And finally, you have the accumulated value that you output. So that's the type signature of fold. So you could do this with a fold. You start with, for example, to compute the sum. Instead of doing data.sum, you say fold left. So let's put this into a block so that these names don't do anything for us. Okay, so how do we compute the n, for example? You fold with initial value 0 and a function that takes, helpfully tells me what it takes. So accumulator and double, let's call it x, going to, well, I'm going to add 1 to b, because that's the accumulator. All right, so that's going to be the length. So I can express those things very easily. So sum is this. Sum squared is this. Right? Why is it int? Int. Right. Now, however, we still, if we combine those, we're still going to have multiple traversals. So the idea that we want to pursue is that we want to have some way of combining these folds automatically into a single traversal. So that we don't have to, well, we could, of course, just do more work and make a single fold which will do all of this. It will accumulate a complicated value. We'll have to accumulate a lot of data. We cannot just do it in a simple traversal like this. We have to accumulate the length separately. We have to accumulate the sum separately. We have to accumulate the average of squares, sum of squares separately. At the end, we will have to perform this computation. So that's kind of difficult. We'll have to accumulate a triple, at least. And then at the end, we'll have to do this. So we could do that by hand. But instead, we want to write some code that will automatically combine folds like these. So we want to basically be able to combine these things together automatically, so that it automatically decides what needs to be accumulated, and we don't want to see all of this. So the first attempt to do that would be just very straightforward. So let's look at what we want to combine. So we want to combine folds. So what's a fold? What is it that we're going to combine? The idea is that this data, the data that you have to pass to fold left, that is what you want to combine. You want to encapsulate this data in a new data type and combine those somehow. And then at the end, you will pass the combined data to the fold left. There will be one fold left at the end. And that's how we will accomplish what we want. Combine the data that fold left takes. So that's the idea. What is the data that the fold left takes? This data consists of two pieces, or two parts. The first part is a value of type B. The second part is this function. Let us therefore define a type that has these two values. I call it fold 0. It has a type parameter B, right? So it has initial value of type B and update function of type B. Let's say BZ going to B. I call it Z just, I don't know. So I need two type parameters actually, right? So this is the signature of fold left. I have a B and I have some type of the sequence element. Both of them need to be type parameters now because I'm trying to generalize this. All right, so let's call this A instead of B because why call it B? Okay, so this is the data that fold needs to perform its operation. Now we can define a syntax to apply to apply the fold operation to data. Right? So we want to be able to define values of this type and fold with them easily. And then we also want to combine them. So let's do one first. Syntax to perform fold left using this data. And that's obviously going to be a syntax extension, right? So it's going to be implicit class fold 0 syntax, some type parameter, which is going to take a sequence of A, let's say, right? Let's just do it for a list, just to save time. Take a list of A and define a function which is going to be called fold 0 of B, taking, actually, let's see, it's here, taking a fold 0 of Z, sorry, A and B, let's get rid of the Z, and the result is going to be B. Right, so that's going to be S, fold left, of fold 0 init, fold 0 update. Done. So now we have this syntax, and now let's define these values. So for example, length 0 is of type, actually what type would it be? It would be fold 0 of some z and say double. Let's just be not very generic for now, but I do need this z. Let's forget about it. Let's not be too generic. It can be done completely generic. For now, the length of a list of double, right? It's going to be fold 0 of 0 and accumulator la going to accumulator plus 1. Right? So that's how we define a fold. And now we can apply data dot fold 0 of length 0. That should equal 10. Okay, I'm going to run this right now before we make a lot of errors. Okay. Done.
So Sergey, what you've done is you've taken this fold operation, what you were originally running as you wrote the code, and now you've stored that operation itself in the case class so that you execute it later.
Right. So I store the data that the fold operation needs.
Right.
And my idea is that I want to be able to combine that data. So that data represents a fold that hasn't yet been done.
Okay.
Right? It's waiting to be applied. And here's, I still want to run this test right now. Okay, that's fast. Right. So this is how I will later apply these folds. Now combine them. So what does it mean to combine? I want to have a fold 0 of ZA. I want to have a fold 0 of ZB. I want to get a fold 0 of Z what? Of AB, maybe a pair of AB. Right? So if I can do this, then I can combine arbitrary folds into a big one automatically. Then I can just apply that. That will be a single traversal. So let's see how we can do this. So the combine function has a type signature that's very similar to zip for lists. So let me call it zip, zip 0. I have fold 0. I'll have fold 1 later, if time permits. Hopefully I will be able to show that because that's also quite interesting. So what is zip 0? Zip 0 is going to take fold 0 of ZA, fold 0 of ZB, you're going to give me fold 0 of ZAB. So I need type parameters ZAB, right? How do you combine that kind of thing? Well, let's look at the type of this fold. So we have a tuple, basically. We have a case class, but this is basically a named tuple having two parts, this and this. So we have this for A and we have this for B. So we have A, we have this function, B, and this function for B, right? We need AB and ABZ to AB. That's what we need. Right? So we just want to return new init and new update. Right? So this is going to be new init, type AB, and new update of this type. And if we can do this, we're done. We have combined it. Now, how to combine this? Well, obviously, there's not much we can do except to combine this A and this B. Right? right? So we have these two. All right, so that's fold 0 init, fold 1 init, right? So that's it. Okay, this is done. Now, how do we do this? Well, we need to return a function that takes this and returns that. Well, let's start writing that function. Case A, B, Z, right? Check the types. Okay. Now we need to return a tuple of A, B. By using those, we can get an A if we have an A and Z. So let's do an F0 of AZ, F1 of AZ. Sorry, F1 of BZ. Right? What is wrong? Oh yeah, F0 update AZ, F1 update AZ. Right. Okay, so in this way, we have returned the correct type. And we have used F0 and F1 somehow by combining them, which makes sense. Now, is that really what we want? Well, yes, because how would this updater work? It will take the previous pair of AB, it will update the first one using the first updater, and update the second one using the second updater. And it reuses the same Z, which makes sense. It's the same sequence we're folding over. So this code encapsulates the idea that we're folding two things at once, but doing only one traversal. Let's now define another fold. So we define length so far. Let's define sum, which we know how to do, right? And let's define sum squared, which is going to be like this. And let's use the zip 0 to combine them. So what will happen? Sum and length, which is going to be zip 0 of sum 0, length 0. Okay? Look at the type. The type is correct. Now it's going to fold and produce a pair. Now let's apply compute average using zip. Right? So I'm going to apply fold 0 of this sum and length. And that's going to give me a tuple, right? Let's call this sum and length 0. And then I say sum divided by length should equal 5.5, because that's the average of this. Yes. Okay? So this is how we succeeded already. We already combined two folds, and there's only one traversal. Of course, this is very ugly. You have to do all this, and this tupling, and all this stuff. And then you have still to do a separate calculation after the program. This is inconvenient. What we would like the code to be something like this, you know, data.fold and then sum divided by length. Wouldn't that be nice? We could have code like this instead. And then we could have here a larger computation. So for example, you know, sum squared minus sum times sum, something like this. You know? Why can't we do it like this? It would be great. It would be very declarative. We can do it. So the way to do it is to understand first that you want this. Once you understand what you want, you design your declarative language, then it's obvious what you need to do. We already know how to combine folds. So all these need to be folds. We just need to define operations that combine them, and at the same time, perform the final computation after the fold. Because so far, our folds always will give you some tuples. We want to combine the tuples in the final computation into a single value. Once we realize that we want this, the natural thing to do is to put that final computation into the fold data structure. Let's define fold 1. So I'm going to define fold 1 by adding a final computation, fold 1, of type A to B. Well, let's call it R, just to be more visual. So A is accumulator, R is result. So we're going to have a structure, fold 1, that encapsulates both the folding and the final computation after folding. So now, if we combine these folds, then this A could be a complicated tuple type, but this result computation will perform all this extraction out of the tuple automatically and give you a single value that you want. So in this case, we will be able to implement things like this. And that, what will be remaining is just syntax, to define syntax for this, which is reasonably easy. So this is the main idea of how to combine folds. Everything else is now just implementation. We need to define, again, the syntax to perform fold left. We need to define, let's do the same things. We need to define the zip, and we need to test that it's working. So let's just do that kind of quickly. So fold 1 syntax will have a fold 1, right? Now, fold 1 still does the same things. It has init and has update, but then it has an extra type parameter, which is going to be ABR, right, for the result. And the result is going to be, so we need this type parameter here. And the result is going to be fold1.result of this. And this is of type R. Okay? So everything else follows pretty much. So double int. Right, so it's going to be int. Well, actually, I could do this, or I could just say it's an int that I accumulate, and then I have identity here. Okay, so let's check that this works. Actually, things won't compile down below yet. Let me make them at least compile, and then I can run this test. Right, now, oh, sure, zip 0. I need a zip 1, which I need to define. And, okay, so oops, sorry, this I didn't mean to screw my previous code. I have zip 1, I need zip 1 here. I need some 1 length 1. And zip 1 needs to be on the fold, and it needs to be ZA-R1. Let's call it A1, R1, with A2, R2. It's going to be A1, A2, R1, R2. Now, the zip still needs to do this. Needs to take a tuple and automatically create, for me, the accumulator type, which is going to be a tuple of what I used to accumulate, and the result type, which is going to be a tuple of what I used to return. Right? Now, let's implement the zip. It's a little more complicated. It's basically the same code as we had for the previous zip, except we're going to have a transform at the end. Right? So it's exactly the same game. Same code will work, except I need to do a new result. Right? So new result of type R1, R2 is going to be F0 result of what? Sorry, what is the new result? It's not the right type. It's going to be A1, A2 going to R1, R2. That's what it's going to be. So it's going to be case A1, A2 going to F0 result A1. Yeah, I'm a 1 result 2. Let me do that. Let me rename for clarity. Done. Now, just for your reference, all of this I have implemented all of this automatically in another file, which I'm not showing here. I have implemented this zip function, zip, automatically using the curryhoward library. Joseph knows about this. It basically implements functions based on the type signature. And the type signature of this function is sufficiently restrictive so that only one reasonable implementation can be found. So the implement is this macro that I have in the curryhoward library. Anyway, let me just show you where it is. It's this one, curryhoward library. So I could just could have implemented all of this automatically. This code is, in some sense, boilerplate. It's boilerplate in the sense that the types dictate what I have to do. There's not much choice I have here about what to implement. All right, let's check that this works. I'm just going to do some squares. I need to have more type parameters here. Hold 1. I need to add identity as a final transformation. Hold 1. All right, done. Hold 1, sum length 1. Let's see if this works. What happened? Duplicate test name, of course. Duplicate test name. Try again. Yes. All right, so it works, but now we can do much better. We can actually define average as a fold. I'm going to skip the types. Actually, these types are not necessary. If I do a zip 1 of sum1 length 1, and then what I want to add a transformation to this. Right? So how do I add a transformation? Now I can. The type of this is this. So I could add a transformation that will take this result and divide. give me a final result. So let's have a function that adds a transformation. So let's do that. Let's do the syntax extension. Do we have a fold1 syntax? Yes, we already have a fold1 syntax. So we need something different. Let's call this fold1 syntax 1. Doesn't matter what that name is for now. Okay, so I take a fold1. So I need these type parameters. And I return something that has a method which is going to be and then some t function r going to t, and it gives me a fold1 of z8t, which is going to be fold1.copy result equals fold1 result and then f. Okay, so that's going to be my code. So I'm going to keep the fold as it is, except I'm going to change its result by appending a function f to it. So now I can do and then some length going to sum divided by length. What is wrong here? Ooh. Double int. Oh, because I already defined sum. What is the type of this? This is a tuple. Why is that a tuple? Oh yeah, because I have to do a case. Yeah, that's why. That's right. Okay, it's done. So now I can do this. I can just compute this average. It is still a bit verbose, right? We have to do all this stuff. So in order to make it less verbose, here's what you can do. Let me just show you the code for the lack of time. Here's what I can do. I can do an arithmetic extension on fold. It's exactly the same fold, except now it's parameterized on numeric result. And if the result is numeric, I can do arithmetic. I can do plus, minus, and so on. And the result is that I can have code like this, where I directly fold, this is a fold1, using this as my combination of folds. And the result is, so the syntax is now almost like we wanted, except I have to put the double in here, because in this code, it's completely generic. It's a generic over numeric type n. Whereas in my example code here, I had double everywhere explicitly. So I don't need any type parameters. But if you want to have your code generic, then that's what you need to do. So you define your syntax, which is, so all this code is going to be in the library, obviously, and your user code will be like this. Okay. So this is how you combine folds into, oh yeah, you can also use scan left with the same data, because scan is like a fold, except you keep all the intermediate accumulator values. And so you can do scan left with the fold data, and in this way you can just use these fold things as to control your scan computations if you need scan. So for example, you can do a running average. The running average is this. So I'm just doing a scan with this average one that I defined, and I get this. So now if I combine several folds into one, I can put them into the argument of this scan one, and there will be one traversal. Well, technically speaking, there are two traversals because I have a map, but I could get rid of that if I wanted to. There's only one, logically speaking, there's only one fold that you're applying. This fold is complicated, and it encompasses the entire computation. So I could express all kinds of things like standard deviation, like that. I can also define pure for fold. So for example, if you look at my plan here, I'm not sure if I will have time to go to the end of this. This computation has folds, but I might need to have constants as well. For example, the standard deviation here requires this constant 1. So I might need to have a constant as a fold that always returns 1. So I can define that. Let me do that here actually for fold 1. So I edit the transformation, define a constant fold. So this is, let me call this pure 1. It's going to be some x, and it's going to give me a fold 1, z r, z r r. So this fold 1 is going to be starting from x. It's going to have a function that just gives me x, and it's going to have a function that returns x. Whatever. It's whatever I want. I just want to return x. I don't care about any of the data, actually. So if I have a fold like this, then I can say, for example, pure of 1 or pure of 2, and I will have a fold that always returns that constant. And I can combine that with other folds, the way that I combine folds, using the zip. And so then I could implement the computations as I wanted. But let me show you, okay, any questions at this point? So we have basically achieved, so with this syntax here, we basically achieved our goal. We can compute like this. What I would like to show you now is that actually this fold is a monad in parameter r. And so you can implement, in a sense, it's not strictly speaking a monad, it's kind of a monad. You can implement flat map, and the only problem with flat map is that flat map could change the type of the fold to some other fold. And so the accumulator type needs to change. Now you might have to accumulate more than one value. So a flat map taken in the usual way does not allow you to change other type parameters. It changes one type parameter, but not others. You would have a flat map in the usual way if you take a fold of r, a function from r to fold of t, and you return a fold of t. However, it won't work because you need to accumulate more data. So you're forced to have a different type parameter at the result. And so this is not really a monad in the sense, it's a generalized kind of monad. But the flat map is a flat map, so it's usable in exactly the same way. So after I implemented this flat map, which again, it's implemented kind of automatically, you just try to see what needs to be done, and you just, first you accumulate the first fold, and then you transform that, then you take the r, you apply the function, you take the second fold, you accumulate that. It's kind of automatic. So the result of this, let me show you this code. It's very, very interesting looking code. I can now write fold combining code in this syntax. Now these are different combinators than the zip, because they can depend on each other. So first I take the average. X is the running average. And then I can define a fold that uses that X to accumulate that running average in another accumulator. And then I also have the length, which is a previous fold. And then I divide this by length. So this gives me a running average of a running average. I have a first fold, and the second fold depends on the first. It depends on the result of the first. I remind you that average is a fold that already computes the result. It divides already the sum by the length. So this is already a complicated fold. And I'm combining it with other folds in here. So using this syntax, it's much more visual, what I do. The result is a fold. And if I apply this fold to a list, I get this, which is, you see, it's growing much slower because it's a running average of the running average. So in this way, I have combined folds monadically, which means the second fold depends on the result of the first one. Using zip, I combine folds in a way that they don't depend on each other. They're all running in parallel when I zip them. But when I combine them using flat map, I can make them run, so to speak, sequentially. A later fold can, this can be an arbitrary updater that depends on the result of the previous fold in an arbitrary way. This X is not the accumulated value inside this fold, it's the result. It's a random result after transformation. So it's a very powerful way of combining computations. And the result of this is still just a fold. It's not yet running. It's just a fold. I don't care about its type here. It's different from zipping. So zipping is the applicative combination, and a flat map is the monadic combination. And so this illustrates the difference between applicative and monadic. Applicative combination means that the structure of the computation doesn't depend on previous results. And monadic combination could depend. And this could be a different fold each time, depending on this X. So that's a much more powerful way, but yet I have a single traversal. So you see this fold, inside it, there's just a single big updater function that is going to be substituted into a scan left, and it's going to be just a single traversal with that updater function. And all of that is automatic. All right, now I'd like to leave time for questions. If anything here needs to be clarified.
Can I see the code for fold 1 again?
Yes. Fold 1 is this. So it is a initial value of the accumulator. It's the updater function, and the final transform from, I'll call it transform, from A to R. So if you look at this type constructor, the type parameter R is in a covariant position, but the type parameter A is not. So it's not a functor with respect to R. With respect to A. So it is a functor with respect to R, so we could make it a monad only with respect to R. So unless we add the transform here, we could do zip like we did with fold 0. But we could not possibly do flat map. Because A, the type parameter A, occurs in a contravariant position here, and in a covariant position here. So zip can be implemented nevertheless. Zip does not require being a functor, being covariant. Zip can be implemented in many cases, but flat map cannot. So you see, I'm using automatic implementation a lot. All of that code is implemented automatically. I'm using also this syntax for functor instance. This is not very important for this presentation. If you feel like, if you want to know about this, ask me. Basically, this has a functor instance, has a monad instance, but only the monad with this type change. So the type parameter in the middle needs to change. Otherwise, you can't perform the code. This is it.
Just given to us by a library.
So there are libraries that implement these folds. There are two that I found for Scala. Unfortunately, none of them are published to me. At the same time, they're very small. There's not much code, rather more than I showed here. Not much more than this. There are some conveniences, there are some predefined folds for numeric data. Basically, there's not a lot more functionality than this. There are maybe some more conveniences. There are some libraries that do this. I don't think it is in the standard library of any kind yet. I'm not sure. I don't think it is. So there are libraries. I would say, well, maybe there aren't so many use cases where you want to combine these folds, but I think it's instructive to look at this to get an idea of what you can do. The basic idea here is that we wanted to combine computations. In order to do that, you first define a data type that represents your computation, but does not yet perform it. So your computation is fully defined and specified, but not yet performed. Then you define combinators for that. So you can combine your computations, and you can combine them as applicatives or as monads. You have a pure, you have flat map, you have map, and you have zip. So you can combine your computations in a variety of ways, and then at the end you run them. Once you have combined all of this, your code is done, at the end you run the computation. So you could organize your program as these computations that are really data structures that are combined in flexible ways, but run at the end. So that's the main idea, and that's what enables this kind of computation. All right. Anybody at remote having a question? If not, we're done. It's 2 o'clock. All right. So that was my folds. I didn't get to talk about parsers, but that's quite similar in spirit. You represent parser as a data structure, you combine them, and you run them. And the question is how you combine them. And in order to understand that, you look for the possibility of zipping them together or flat mapping. And you know how to deal with those. Once you define those, you go, do you have a pure? Do you have a flat map? Do you have a map? Do you have a zip? And once you define that, you're done. You just combine in a very flexible way. You combine all your computations. You have a domain-specific language of sorts. And then you run it in the end. All right. Well, we're out of time. Thank you very much.
Thanks, Sergey.
Thank you.